All right, this is lesson 16, the QDA, or the quadratic discriminant analysis. What we're going to start is where we ended off last time. So we ended off with linear discriminant analysis, or LDA, and most of the stuff that we did in that lesson applies to this lesson. So I'm not going to rederive some of the equations, but just note that we used Bayes' theorem to change the order of the conditional probability here. We want the probability that the random variable y, or the class of the of the new observation, is in class K, given that x is equal to x. And we say that's proportional to, because we got rid of some of the stuff, the law of total probability stuff at the bottom. It's proportional to the prior probability, and all that is, if you remember, is just the proportion of each one of the classes that are in the data. So if you had, for example, I'll just do it in pink over here. If I had 0, 1, and 2, say I had 3 classes and I had 3 of those, 4 of those, and 2 of those, I would say that the prior probability, or pi 0, would simply be 3 divided by, was that 7, 8, 9, 3 over 9. Pi 1 would be just a proportion, meaning we don't have any other information. And pi 2 would be 2 over 9. 4, 6, 7, 8, 9. Yeah, just making sure they added up. So that's the prior probability, and then we take the natural log of this distribution, knowing that we assumed that x came from a normal distribution. And when p is equal to 1, it's a single variable normal distribution where you have a single number representing mu k and a single number representing the variance. When p is greater than 1, p being the number of predictor variables, then we assume that the random variable, the random vector x, comes from a multivariate normal distribution where mu is now however many predictor variables you got, right? So I got a mean for each one of those predictor variables, and then I have a covariance matrix that goes along with that. So if you did this in the single variable world, it would look this way, and then we'll get to the multivariate piece in a second. But in the single variable world, and when p is equal to 1, the next thing is, so that's what we would get, and then we make this assumption that all of the variances are equal, so that you have this common variance called sigma squared, and that gets replaced in here and replaced in there. And so what happens is these two terms basically go away because we don't need them anymore, because they're the same for every single one of my classes, and therefore all I need to do is calculate this value and then pick the class that has the largest one of those numbers, and that would be a sort of synonymous of picking the probability of being in that class given x is equal to x. So that's the linear discriminant analysis for p equals 1. And then what happens when you have a vector that goes in here. In other words, you have more than one predictor variable, and you're using this multivariate normal distribution. It looks like this, and so this is how you do this multiplication. So remember, this is variance, and it's in the denominator, so that's why you get that sigma inverse. And then I'm going to take one of the two vectors and put them on the outside and transpose it, multiply by this. So if you did this, this would come out to one number. I'll just give you an example here real quick. So here, let me do it in pink as well. So suppose that p is equal to 2. I'm just going to show you in p is equal to 2. So my mu, my x, let's just give an example of maybe what x is 1, 1. And maybe mu k is 2, 1. Then and then sigma inverse would be some I don't know. I got some really good imagination here. 1, 2, 3, 4, right? Because it's going to be a p by p matrix. So what would this calculation look like? Well, it would be 1, 1, which is a 1 by 2, and then a sigma inverse, which would be a 2 by 2. And then this thing would be 2 by 1. And just note what happens, right? And this is a 2 by 1. So those two all lines up, and you were just left with a 1 by 1, which is a scalar. So just recognize that's going to be a scalar, this is going to be a scalar, and so on and so forth. So, and that's what we're looking for. I want to be able to compare a number to for each class and pick the one that's the largest. Okay, that was last class. All of that was sort of a review, sort of the bottom line. How do I pick a class? You know, if I'm given 3 classes here, then I would have a different mu k or a different mu k vector mu k. I'd have a different for each one of these classes. I'd have a different sigma. I'd have a different sigma squared here. So that's how we go about, and then we just substitute it in and pick the one that's the biggest. Whichever one of my deltas here that was the largest, that's the class that I would pick. And I think I'll give you an example here in a second at the bottom just to recall what we're doing there. Okay, today we take away that assumption. So remember the assumption that these were equal. I guess I could highlight it real quick. That is no longer true. So that part we're just gonna say nope, goes away, and we're simply left with this thing minus, I think there was a 2 pi in here, but again, if you're doing the same thing to every single one of these deltas, then it's not going to change the ordering, and really all we really care about is the ordering. So now the reason why this is quadratic, so just remember the reason why this was linear was it's linear in x. So that's still linear in x. It's I forgot a squared, I believe. Let me make sure. Yeah, I forgot a square here. Yeah, that would make a difference. Oh, yeah, it's right there. So that square should have came down, and that's why you did the vector transpose sigma times the vector. Okay, let's see. So the reason why this one's called quadratic is I can no longer get rid of this because it's not a common sigma, and so this term remains, and so we're quadratic in x squared. And then down here, this is also a quadratic term in x. So again, just taking the delta, this should be exactly the same as what was written up there, except for the 2 pi's there now, and you can't do any of these cancellations. And so just to turn this into a multivariable, when we're assuming a multivariate normal distribution, this stays the same. This one stays the same, except instead of having the variance here, I'm going to take the determinant of the covariance matrix, and then minus 1/2, and then we split this x so that we can actually do the multiplication and get a number out of it. So x transpose sigma inverse, or sigma k inverse x, and so on and so forth. So this is sort of the calculation. Again, this is going to come out to a scalar that I can compare each class to. So let's get an idea of maybe what that might look like. So suppose I think here I have 4 classes. Class 0 is the pink one, class 1 is the yellow, class 2 is the red, and then class 3 is the blue. And what I did, and these are all, I guess not all of them are separable because I threw a pink inside that one. But basically this is, we know what these classes are, we know where the data points are at, and we know what the covariance matrix is. Here I know class 2, you know, it's got a smaller covariance matrix, but it's kind of turned in that direction. Class 1 kind of looks like a circle. I mean, these should be perfect ellipses, but I'm not really good at drawing those. And then I give an example for mu2, mu1, sigma, so mu0. So again, all I did was I said 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's about 9, and then 1, 2, 3, about 3.5. So I figured that's what mu0 is. Again, and if we push this thing back, maybe it would be, but just understand that you know, these numbers that I'm coming up with are just to give you a hint or give you an idea what's going on. So pink has its own mu, and red has its own mu, and they also have their own covariance matrix, and this one would have its own covariance matrix because it would be down here, and it'd be kind of these would be close. This one would certainly be different because it's more of a circle. This one would be pointing in a different direction. So just understand that each one of my classes has its own covariance matrix that goes along with it. So what would I do? I would take this equation right down here, and I would do for each class, like for the pink class is the first one, I would take my new point 6,3. I just kind of made it up here 6,3, and I'm sticking it into this function, and then we're going to take for class 0, I'm going to take 935, and you can see 935, and then I take whatever the estimate for the covariance matrix would be, we put that in here too, and again it would come out to a scalar. And then we do the same thing for take same 6,3, put it in this delta 1. Well, what do I mean by that? We'll go find all the yellow stuff, right? So I'd use 7.4 instead of 935, and I'd use whatever its covariance matrix is instead of this covariance, it's sigma 0. So again, it would come up to a number. And then we do the same thing with delta 2 and delta 3. And then you can take those three numbers and compare them, and whichever one's the largest would be the class that I would classify that one as. That's all it is. It's the same thing as linear discriminant analysis, right? Same thing up here, except just a different delta that we're using. This delta assumes that some of those sigmas all go away, and in this case, we can't use that. All right, so let's program it. Let's actually use Python to do this for us instead of trying to do all this by hand. So let's go back up. So the first one that we're going to do is called the menace data. It should be in your CoCalc. This sheet should be in your CoCalc. And what you're going to have to do is download it, put it on your computer, and then find the menace train on the course website, pull the train.csv and the test.csv, and then put it into a folder you can find it on, and then let's go from there. So let me pull in all my modules that I'm going to use for this lesson, and then I'm going to pull in the data, and you'll see that it'll take a second to bring it in because there's 60,000 training data pieces of data, and there's 10,000 test pieces of data. Okay. So now what I want to do is I'm going to show you what's in each one of these data frames, because I just brought them in as data frames. And there's an easier way to do this. I think I'm not real sure what I was trying to do here, but you could do an MShow on, yeah, there's probably a really, really quick way of doing this. So, but what I'm going to do is I'm going to use this thing that I created in order to display it. So we'll do display image, and then we'll put in train.iloc, and then I want row, just you got to pick a row, I don't know, row 0, and then 1, so all the columns. So the way this here, matter of fact, let me add another row here, and I'm going to show you what this thing looks like, right? So what it is this first column here has the actual, so that's this data represents a 28 by 28 image, and it should look like a 5. These numbers, like that would be white, 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 and then whenever you start getting numbers between 0, there should be some in here that are like 255, and they represent pixel colors between 0 and 255. So in other words, if it's really dark, then it would be 255, it would be pitch black, and then any number before that would be sort of a grayscale that goes along with it, except for this first number. So let's see what that looks like. Let's see what row 0 looks like, and apparently it's a 5. And that's exactly what it's saying. So it's telling you that I want you to train this set of pixels to be a 5. And I want you to train the next set of pixels. So let's get the second row to be a 4. Oh, no, I guess I did 2 instead of not the second row. I did the third row, which is the 2th row. And it would be a 4. Let's see, hopefully 1 looks like a 0, and it does. Okay, so that's what we have to work with. So let's determine how many of each. Okay, so how many? So data set. I want to know how many of each class. Obviously, I have classes 0, 1, 2, 3, 4 through 9, right? So these are all of my digits, and then I want to do a value underscore counts. A little bit of data. Just kind of looking at what's in our data. So if you added up all these, it would be 60,000. You can see I got 6,700 ones and 5,400 fives and some number in between each one of those. So now we're going to make the train and test data. I'm going to make it out of this. So I got to do xtrain is equal to data frame dot iloc. Oh, no. I got train. So train dot iloc. And then I want, I got to capital here. So xtrain is going to be train.iloc, and I want all the rows, and then starting at column 1 all the way to the end. And ytrain, right? My response variable is train.iloc, and then all the rows in column 0. And then xtest is the same. Should be the same thing except for test data frame instead of train data frame. Test print length x train length of y length of x test length of y test 60 60 10 10. Okay, so I think what we've done is we separated this into our train data and our test data exactly the way we like to see it. And then I'm going to use it and we're going to train it on linear discriminant analysis. If you remember, I don't know if I don't think I did this yesterday or the last time. So DA, so where am I getting DA from? So I pulled in the scikit-learn discriminant analysis packet that's in scikit-learn, and then I'm calling it DA. And so I'm going to say DA dot linear discriminant that will be my model.fit. We're going to put in x train and y train. So the real question here is what's happening when I execute this? Think about that for a second. What is going on when I do model.fit? When I do model.fit, I will say that in class, no one had the answer for this. So think about it for a second, and now I will tell you. All it's doing is it's calculating, when you do model.fit, it's going back and it's calculating these things, right? So it's calculating my mu2, it's calculating my covariance matrix for that. It's calculating class 3's mu, it's calculating class 3's covariance matrix. So really that's all you're doing when you do model fit. And then when you do predict, then what it does is it does this business where it calculates these deltas and then classifies it as the highest. But it already has sigmas and the mu's in it, right? Because it's already fitted. So model.fit, and then what do we want? Y hat equals model. So now we're doing the deltas because we've just calculated everything that we need there. And you got to pass in x underscore test. That now we can print accuracy equals score y test. Print confusion matrix. I think we call it C matrix up there. You can check out, just go to the top, and I called it as C matrix. So my confusion matrix, instead of writing this whole thing out, I just called it C matrix. And now let's see, C matrix, and you got to put in Y test. This will be the row, and this will be the column. Out. So it's doing all its business. And eventually we will get so an 87% accuracy score. And remember how the confusion matrix works. These are the actual, so this is the actual zeros, and then this is what you predicted for those actual zeros. So 940 actual zeros I predicted to be a 0, and then no ones, or 0, 1, no 1, 2 I predicted to be a 0, 1, 4 3s, and so on and so forth. You can kind of see the ones that confuse you, if you will. It's okay that this pink thing came out. I mean, this is a picture. There's nothing I can do about it. I'm not getting rid of any columns. And then the next one is to do quadratic. So it's just so easy to do quadratic analysis on it because you just kind of do the same thing except for changes linear to quadratic. And hit Shift Enter. It's doing the same business. And you get a much lower score, and you can kind of see where it messed up. So it looks like everything's being predicted as a 0 in the quadratic analysis. So a further study is probably needed in order. I believe it kind of gets confused with some of this collinear data, but just understand that you know, these are two of the options out there. I'll let you guys finish the vehicle of death. I'm not going to sit here and go through that, but I've given you a lot of the code that's in there. And then there's a fashion miniset data, and then a car choice. I mean, there's there's lots of data out there that you can use. Just understand that you know, what you have under the hood is really what's important, right? What are those? What is going on when I do dot fit? What is going on when I do dot predict? That is what I want you to understand. All right, that's all I got for this lesson. I hope you guys got something out of it, and I will see you next class.